Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying Quadratic Lecture 3. In this lecture, we'll be studying the most difficult topic of quadratic, that is location of roots. Okay, so let's begin our lecture with the case 1 of location of roots, and in total we are going to study 6 cases. So what are these cases? These cases are nothing but statements based on which we have to find out conditions such that the quadratic expression aligns with the given statement, right? Before moving forward, we'll be following certain rules and guidelines and protocols, right? Based on which we'll be solving or deriving these conditions. So the first thing is we'll always be using quadratic expression as ax square plus bx plus c, roots as alpha and beta. And lastly, we'll always be starting with an upward facing parabola and then we'll involve downward facing parabola so that we can find out a common condition for both of these, right? So that's how we're going to do. So now let's first talk about case 1. It says both roots are greater than x1, right? Now the first thing to notice over here, both roots, right? And we're comparing them with a real number, that is x1. Now can we compare a complex number with the real number? No, we cannot do that, right? So that's why d is either positive or c equals to 0. In both the cases, we have two roots. In this case, two roots as equal. In this case, two roots as distinct, right? So there is no mention that the roots cannot be distinct or equal, right? So that's why we have taken both the cases. But definitely d cannot be less than 0 because we cannot compare complex numbers with a real number, right? So that's clear. So our first condition is d is either positive or equals to 0. That is our first condition. Now given that d is either positive or equals to 0, we can have parabola on the right hand side of x1, we can have parabola containing x1, we can have parabola on the left hand side of x1. All these three cases are possible. Why? Because this is a generic statement, right? It just says it has two roots or one root, right? So x1 can be anywhere. Now we have to eliminate this one and this one, this case and this case. Why? Because in this case we can see that both roots are greater than x1. This is what we want in the condition, right? So that's why we have to take this case and eliminate these two cases. How do we do that? The basic idea that comes to our mind is we can just simply say alpha is bigger than x1 and beta also bigger than x1. In that case our condition would be true, right? But that's not very simple. Why? Because if we write down roots for this equation, we'll be getting alpha, let's say, as minus b plus under root b square minus 4ac divided by 2a, and beta as minus b minus under root b square minus 4ac divided by 2a. Do we want to solve these inequalities? It's impractical to solve these kind of inequalities because we have roots over here and it's very difficult to solve these kind of inequalities, right? So we have to do something simpler. Now let's say we have this case over here, we have x1 over here, this is alpha, this is beta. Now if you remember that this lowest point, let's say this is vertex v0, okay? Now if we find out the x coordinate of this v0, that would come out to be alpha plus beta by 2, right? And that actually comes out to be minus b by 2a for this quadratic expression ax square plus bx plus c. V0 equals to alpha plus beta by 2, that comes out to be minus b by 2a, right? That is exactly at the center of alpha and beta. Okay, now if we say that v0 is bigger than x1, can we say that our conditions are getting true? Still we cannot say that. Why? Because if v0 is bigger than x1, then we can also have a case where x1 is over here and v0 is over here, right? In this case, x1 is inside the parabola. We don't want that case, right? And still v0 is bigger than x1. So we have to add one more condition, right? How do we do that? So our second condition comes out to be v0 should be bigger than x1, right? We have to add one more condition. Now let's draw two cases over here. Now the first case is this is our v0, this is our x1. In second case is this is our v0 and this is our x1. In both the cases, this condition is getting true, this condition also getting true, right? We have to eliminate this one, right? To get the final answer, we have to eliminate this one. Now, what is the major mathematical difference between these two graphs? In this case, if we take f of x1, that would come out to be positive. In this case, if we take f of x1, that would come out to be negative. How? This is x1, So this function would take a value somewhere over here, that is positive. In this case, it would take a value somewhere over here, that is negative, right? So that is the major mathematical difference between these two graphs, right? So what we can do, if we eliminate this condition, then we'll get this condition automatically. So our third condition would be f of x1 should be positive, right? That's our third condition. Now, until now, what we were doing, we were just talking about an upward facing parabola. And if you remember the protocol, we wanted to include both parabolas, right? Downward facing or upward facing, because we don't know the value of a, right? A can be positive or a can be negative. We have just considered one part of the equation, right? We have just considered the upward facing parabola. We have to include both type of parabolas. Now, in downward facing parabola, this is our x1. Now if we talk about d is positive or 0, this condition is true, right? This condition is directly applicable over here. If we talk about v naught is bigger than x1, again that is applicable directly over here, no change. But the third condition, f of x1 is positive, in that case f of x1 would be negative, right? In this case f of x1 would be negative, but in that case we'll have to apply two conditions two times. First this set of condition, and secondly that set of conditions, and that would make the problem solving a lot more lengthier as compared to what it should be. So there has to be some common ground between these two conditions, right? Between these two types of parabola, there has to be some common ground. Okay, so now what we can do, let's compare both the graphs, right? Both upward and downward facing parabola, so that we can find out a common point. In this case x1 is over here, in this case x1 is over here. Here a is positive, here a is negative. Here f of x1 is positive, f of x1 is negative. Now that gives me a trigger. What if I write a dot f of x1? Now this comes out to be positive in this case. And if we write a dot f of x1, in this case, it also comes out to be positive. So that is our common condition. So rather than writing f of x1 for positive for a positive and then f of x1 negative for a less than 0, we can directly write a dot f of x1 is positive, and that would incorporate both these types of parabolas, right? These two conditions are common for both of them, and rather than this one, we can write down this third condition, a dot f of x1, that is positive. That would give us the final answer. So our third condition, final condition, would be a dot f of x1 should be positive. Okay, so this is our third condition. So first condition is d is positive or 0. Second condition is v naught should be bigger than x1, and third condition would be a dot f of x1 should be positive. Now, I could have given these three conditions directly to you without even deriving them, but that's not practical, that's not logical. Why? Because first of all, we have 6 cases. It's very difficult to remember conditions, different conditions for all 6 cases, and it's very likely that you are going to forget one of the conditions during the examination, right? So it's very important to understand the thought process behind these conditions, so that in case you forget the conditions in the examination, you can derive them directly over there, right? And now let's move forward to case 2, that is the exact replica of case 1, right? In this case, what we have roots alpha and beta smaller than a given number x1, right? In the previous case, we had alpha and beta bigger than x1. In this case, we have alpha and beta smaller than x1. Same thing, right? Same thing. So if we want to derive the conditions directly over here, we can simply write d should be positive or 0, right? That is the first condition. Second condition would be our v naught should be less than x1, right? In that case, our v naught was bigger than x1. In this case, v naught should be less than x1. And third condition would be a dot f of x1 should be positive. Same condition, right? Over here we have alpha and beta, and we have x1 over here, right? So that would be positive. This is for a positive. So a dot f of x1 should be positive, right? So we have these three conditions over here, which is the exact replica of the previous case, just that we have this minor difference over here. Okay, now let's talk about case 3. So we have one root greater than x1 and another root smaller than x1. Okay, so we'll start from the basic ax square plus bx plus c, and roots as alpha and beta, right? And we'll start from the upward facing parabola. This is alpha and this is beta. Now x1 should be somewhere over here in between alpha and beta, right? Because alpha, that is one root, is smaller than x1, and beta, that is other root, that is bigger than x1, right? This is what we want in the condition, right? Now how do we derive this one? So the first condition that looks very obvious, that is d should be positive. We have to have two roots so that this condition becomes true, right? Because one is bigger than and one is smaller than, right? So we have to have d as positive to get two distinct roots. We cannot have d equals to 0. If d equals to 0, this condition won't be true. So we have to have d as positive, right? That is our first major condition. Now, if you look at it closely, in this case where a is positive, we can simply say that f of x1 should be negative, right? F of x1 should be negative because if x1 was here or here, f of x1 would have been positive, right? In this case, value would have been here. In this case, value would have been here. Both are positive, right? But in this case, since x1 is inside the both the roots, in that case, we can simply say that f of x1 should be less than 0. That is our second condition. F of x1 should be less than 0. But again, we have to incorporate downward facing parabola as well, right? We have to incorporate downward facing parabola, right? So in downward facing parabola, we can simply see that f of x1 is positive. So what is the trick to find out the common condition? We have to multiply a. In this case, is a is less than 0. In the previous case, a was positive. So when a was positive, f of x1 was less than 0. When a is negative, f of x1 is positive, right? So what do we do? A dot f of x1, that should be negative, right? A dot f of x1 should be negative. That would incorporate both these parabolas, both these types of parabolas, right? So our second condition, second major condition would actually be a dot f of x1 should be less than 0, right? Now, under these two conditions, can we draw any other type of parabola which is not adhering to these conditions? No, we cannot do that. X1 should be here. This is alpha. This is beta. A dot f of x1 should be negative, and both roots are distinct. Okay. These are the only two conditions for this particular case. And now let's talk about case 4 where we have both roots between x1 and x2. So let's start from the basic. We have ax square plus bx plus c as the quadratic expression and alpha and beta as the roots, right? Now let's start from an upward facing parabola. So we have this x1 and x2. This is alpha and this is beta, right? Now the first obvious condition is t should be positive or equals to 0. Why 0? Because regardless of what alpha and beta is, they can be same, they can be distinct. They should be between x1 and x2, right? They should be between x1 and x2 regardless if they are same or distinct, right? So that's why we can have d should be either positive or equals to 0, right? That's our first basic condition. And now that we have x1 and x2 over here, our next set of condition would be f of x1 is positive and f of x2 is positive, right? So second condition is f of x1 is positive, f of x2 is also positive. That is third condition. Now here's the catch. Let's say if I take x2 over here, can we say that f of x2 would still be positive for this case, right? In this case, f of x1 is positive, f of x2 is also positive, but we don't have x1 and x2 encompassing alpha and beta. Alpha and beta are not between x1 and x2 over here, right? But still we can say that f of x1 is positive and f of x2 is positive. So that's why these conditions are a little flawed. We have to add additional condition over here, right? How do we do that? For that, we can simply say that this is our v naught. So fourth condition would be v naught should be less than x2 and bigger than x1, right? If that is happening, we can simply say that x1 is over here and x2 is over here, right? So we have to do these four conditions for this particular case. So this is one of the most difficult case over here where we have to apply these four conditions. So our basic idea was basically we started from d either positive or equals to 0. Then we used x1 and x2 for fx1 and fx2, and then we used v naught so that we are ensuring that x1 is outside and x2 is also outside the parabola. Okay. Now what is left in this case? We are leaving behind the downward facing parabola, and I'll keep that as homework. You have to find out the common conditions between the upward facing parabola and the downward facing parabola, right? For this particular case, right? And now let's talk about case 5, which is one of the easiest case. Okay. So we have exactly one root between x1 and x2. So let's start from the basic. Ax square plus bx plus c and alpha and beta is the roots, right? So we again start from an upward facing parabola. So let's say x1 is over here, x2 is over here, and this is a root alpha. You can also have a case like this one where x1 is over here, x2 is over here, and this is our root beta. This is alpha and this is beta, right? Now in this case, we can see that f of x1 is positive and f of x2 is negative. In this case, f of x1 is negative and f of x2 is positive. Now, what if we multiply both of them? f of x1 dot f of x2, that comes out to be negative, right? In this case as well, and also in this case, in both the cases, f of x1 dot f of x2 comes out to be negative, right? Now, what if we want to try this for a downward facing parabola? Let's say we have this downward facing parabola. This is alpha, this is beta, this is x1, and this is x2. I can see that over here f of x1 is positive and f of x2 is negative. If we take the product of both of them, we'll still get f of x1 dot f of x2 as less than 0. So we can see that this one condition is common for all types of parabola. Now you must be wondering, why haven't we applied d as positive in this case, whereas in rest of the cases we have applied either d as positive or equals to 0, but not in this case. Why? Because when we are saying f of x1 is positive and f of x2 is negative, that automatically means d is positive. How? Because this is only possible when we have two distinct roots. If there is just one root, we cannot have f of x1 is positive and f of x2 is negative. We cannot have, right? We cannot have even this condition. So it has to have this condition as automatically true when we are saying this one. When this is true, it automatically means that d is positive. It automatically assumes that. So all the cases where d is positive comes under this condition only. So that's why we have ignored this one. This becomes redundant, right? And now we have case 6, which is the last one, where we have both roots outside x1 and x2. And I'll keep this as homework because I think I have built enough intuition and thought process on how to drive these conditions without having to remember them, right? So I'll keep this as homework. So this lecture ends here only, and in the next lecture, we'll solve certain examples for location of roots, and also we'll do the last topic, that is common roots. So let's meet in the next lecture. Thanks for watching.